It's nice to be here. Last time in Pisa was in 2019. It looks like ages. A lot of things happened meanwhile. Now we are back. So this talk is about non-equilibrium properties of nonlinear lattices, more from the point of view of steady states and steady state transport. So it's in a sense complementary to what you have heard before about transient processes. The motivation for this type of studies are very many. I mean, and I just summarize what are the main findings of many years of research that I did together mostly with Antonio and Roberto. And the idea is that when you study these nonlinear lattices in reduced spatial dimension, for example, one dimension, typically you observe violations of standard diffusive process, like, for example, the famous Fourier law. So what happens in a nutshell is just that the usual heat equation must be replaced by something different, which is typically a super diffusive type of equation. Today I want to talk about how this scenario changes when we are close to an integrable limit. So what happens when you consider a system that has a macroscopically large number of conservation laws? And I will talk mostly about the famous TODA system. So this is just a book in which you can find a review of many topics I will talk about. So that just the type of system I have in mind is a chain of coupled oscillators, nonlinear coupled oscillators. Think about the famous Fermi-Pascagoula model and something like that. So what is important in these models is that we have, if V depends only on the relative displacement, we have three conservation laws, exactly like in a standard one-dimensional fluid. We have three conservation laws that can be written in this way. One is the energy, of course, for the isolated system. The other is the momentum. And the third one is slightly less trivial. You can think as the equivalent of the conservation of density. Or in another way, a conservation of volume. The fact that if you keep the system in a finite box, it will occupy a volume which is fixed. So the macroeconomic equilibrium of this class of models is determined by these three quantities. The examples are, for example, as I mentioned, the famous Fermi-Pascagoula model, where the interaction potential is an algebraic potential. This is a model that has been studied a lot. There are two types of models. One is the one with where the leading nonlinearity is cubic. The other is the one in which the leading nonlinearity is quartic. So the case G3 equals 0. And these two models may appear similar, but they are different, and I will comment on this later. So what we want to study is non-equilibrium properties and steady state properties of these models. And typically what you do is something that corresponds to an experiment in which you put the system in contact with two reservoirs at different temperatures. So you heat on one side, you cool on the other side. You wait enough, time long enough, and you expect to have a steady state in which there is an energy current flowing through the system. In this way, you can measure an effective conductivity as the ratio between this average flux and the applied gradient that you impose on the system. Now, it turns out that for this kind of system with three conservation laws, you have these anomalous properties, which means what I mentioned before. Just focus on the first two. The first one is the fact that the conductivity that you measure with this method is basically ill-defined in the thermodynamic limit. So instead of being a constant, a material constant like it would be in the standard case, it's something that diverges for very large sizes. So it means that the conductivity is infinite in the thermodynamic limit. This is just a facet of the very well-known long-time tail problem. I don't know if you ever heard about it. It's a famous thing. The fact that the correlation functions of the currents decay very slowly. So they decay so slowly that you plug them, when you plug in the Green-Kubo formula that give you the transport coefficients close to equilibrium, this integral diverges. And this is what is meant by long time tail. So it means that the process cannot be described in terms of a standard diffusive process. Now, the main message is that for the models of the class that I showed you before, like, for example, the Frey-Pastaula model, typically this is what happens in one dimension. So typically, transport is anomalous, we have these long time tails, and we have an infinite conductivity. There is a theory behind this, which has been developed mostly by Herbert Spohn. We also contributed to it from a different point of view. And the idea is very simple. It's the usual hydrodynamic approach. So what you do, you have three conservation laws. You write the evolution equation for three fields, which correspond to fluctuations of energy, momentum, and density. And then you add perturbation to this to the first order linear terms, which are nonlinear, and look what is the effect of these nonlinear terms. Now, it turns out that there is a very interesting connection between this type of, this is called the nonlinear fluctuating hydrodynamics theory, because you have nonlinear terms and you have noise added. It turns out that this hydrodynamic theory is just a vector version of the famous Kardar-Parisi-Zhang equation, which is also known as the Burger's equation. So this is a very important equation in non-equilibrium statistical physics. It has been introduced in a completely different fields, but it turned out to have an amazing large of a number of applications in many different fields. And in this context, what does it mean? What it implies exactly what I tell you at the beginning. It implies that the autocorrelation typically decays like t to the minus 2/3, which means that when you integrate this quantity, as you would do in the Green-Kubo formula, this quantity diverges for t large, because this power is less than 1. So what you have is that if you plug this expression in and you use it to estimate the finite size conductivity, you find that the conductivity must diverge like L is the size of the system to the power of 1/3. This result is very robust, so it doesn't depend very much on the detail of the interactions. So you may have different type of nonlinear potentials, different type of forces, but on large time scales, if this hydrodynamic approach holds, the results should be the same. So this is in a few words the result of many years of studies about these non-equilibrium properties of these chains. Now, the point of this theory is that it assumes somehow that the system thermalizes and there is a fast, let's say, relatively fast randomization of energy, momentum, and so on. So in a sense, the system must be strongly chaotic. So one question is that comes naturally is that this type of theory will not apply, of course, in a situation in which I have for a system a completely regular dynamics. And the extreme of this regular dynamics is constituted by an integrable system. An integrable system is a system that has n degrees of freedom and n independent constants of motions. So in this case, the dynamics is absolutely regular, because once you fix the initial actions, the initial conditions, this quantity will remain constant forever. There will be no mixing, no thermalization, anything. So in the context of the class of models I'm studying, the most famous example of this system is the Toda chain. The Toda chain is exactly the type of model that I showed you before, with this particular potential, which is exponential in the relative distance. This is well known. It's a very famous model studied in the 70s of last century. And it was proven by a lot of methods that indeed there are as many constants of motion as degrees of freedom. These constants of motion have complicated expressions in terms of the canonical variables, but nevertheless, they're there. So how, there is another model that I will consider, which is in a sense the infinite energy limit of of the total chain. So if the energy is very large, you just explore the exponential part, and in practice it's like having hard point collisions between particles. So you can consider an extreme case in which you replace this exponential with a kind of infinite barrier. And of course, if the masses are equal, you see two particles collide, they just exchange the velocities. So the set of initial velocities remains constant during all the motion. So this is the simplest example of an integrable system. So, this figure is completely unreadable. Now, you may think that from the point of view of transport, you may think that more or less that for an integrable system, the situation is trivial. You have particles, quasi-particles. They are independent. No? They just propagate freely through the lattice, through your volume. And basically, it's like having a free gas. This is true, but not completely true. Huh? And you realize this, at least you would have realized if you could have seen this figure in a better way. If you compare exactly the two models that I presented, what is the hard point chain, the model with the hard point particles colliding, and the other is just the toda. So in the hard point model, when you have two particles that collide, they just exchange velocity. So you can just relabel your particles and imagine that there is one particle that moves with the same velocity from one side of the system to the other. So this is really a free gas, no doubt. So in this case, you are entitled to think that the quasi-particles are really independent. The situation is different for toda, because now you don't see anything. But if you label a toda soliton, and you try to do the same type of thing that you did with the previous model, you see that actually the soliton moves ballistically, but it undergoes kind of shifts at every collision. So when it meets another soliton, it keeps the same energy and momentum, but it shifts a bit the phase. So it's like having it's not a real diffusion, but it's certainly a perturbed motion. So in a sense, the motion is ballistic at the end, but it is not purely uniform motion. And this leads to the distinction between these interacting and non-interacting integrable systems. So toda would be an interacting system in this sense I explained you. The hard point gas would be a non-interacting system. So what I'm going to, just to put the thing in a context, there is a renewed interest in the integrable systems, especially from the point of view of statistical mechanics, because as you may imagine, toda chain has been studied in hundreds of papers, but most of the papers, not to say all the papers, were at zero temperature, basically. So what you study is typically you put the system at rest, you initialize with the solid, and you study the scattering to solids and so on. So much less is known, and I would say almost nothing was known, when you put the system at finite energy density, finite temperature. So you want to study a statistical mechanics problem. This has been studied very recently in the context of what is called the new generalized Gibbs ensemble, and the idea is really simple. If you have n integrals of motion, you have to define an ensemble in which you have n Lagrange multipliers. So it's a complicated ensemble with respect to the canonical and grand canonical, in which you have as many temperatures or chemical potential to fix as degrees of freedom. No? And this idea was used because it was possible to implement this idea to construct an hydrodynamics of integrable system, which is a novel approach which has been pursued, and it's great interest, especially in the community of many-body quantum systems. So, from the point of view of transport, what is the main feature? So, I said that integrable systems should behave more or less like free particles, right? So, it should be ballistic transport. So, you should have something like particles that travel from one side to the other. So, how does this manifest, for example, in the statistical description of the system? Well, it manifests in the fact that the correlation function of the energy current does not go to zero. For a chaotic system, for a normal system, you expect this correlation to go to zero. For an integral system, it doesn't. Which means that somehow the current is roughly constant. at least on a larger time scale. Now, the mathematical formula to study these properties is called, if this quantity goes to a constant, when you Fourier transform it, so you go to the frequency domain, you expect to have a delta contribution at zero frequency, no? The Fourier transform of a constant is a delta. So the strength of this delta, this D, is called the Drude weight. So if you want to study an integrable system, you have to learn how this Drude weight behaves with your parameter in the GG ensemble. There is a way to study this. It's called it's based on what is called the Mazur inequality. I don't enter to this, but just the idea is that you can estimate a lower bound for this Drude weight by computing the correlation, the static correlation between the current and the conserved quantities. This in principle is true in general, so it's also true for integrable dynamics. And it can be used indeed to estimate this Drude weight for the total chain. It's not easy because as you have seen, the conserved quantities are complicated functions of the canonical variables, so it's not technically easy, but in principle it can be done. This is just a test that has been presented in the literature. Okay, so I think we can go on. So the idea is that for this integrable system, you have indeed this infinite limit of the correlation that doesn't go to zero. But you have another feature which is less clear, at least less trivial, the fact that the correlation function goes to this constant with some law, and this part, so this relaxation of the correlation constant is exactly connected to this process of interaction of this quasi-particle that leads to this scattering that I show you in the figure before. So there is a form of irreversibility also in this process, also for an integrable system. So the situation is a little bit more complicated than one would naively expect. Okay, so this was more or less a review on integrable systems. So my question was, suppose I have an integrable system and I add a small perturbation. So I take for example, the Hamiltonian of the total chain, and I add some H prime. So in principle, I could have what are the consequences of this on transport properties? So in principle, I can have two situations at least. If this perturbation H prime destroys all the conserved quantities, except, for example, the energy, which has to remain, okay, what should I expect? Well, I should expect to have a diffusive transport, because I know, I didn't say it, but I know that usually in this situation, the system will display diffusive transport. So it would be a normal conductor in a sense. On the other hand, if I destroy all the conserved quantities, except the 3-1 that I mentioned at the beginning, so if I conserve this momentum and this volume or density or stretch, that's several names, I would expect to fall back in the KPZ universality class. So to be in the same universality class, to have the same type of anomalous behavior that I observe, for example, for the FPU model or similar. Okay, this is the expectation. This is true. I mean, this expectation is correct, but there are several subtleties. Okay, the first subtlety is the here. There's really nothing. The first subtlety I just mentioned very quickly is the following. The form of the perturbation matters. So even if you keep the energy constant and you destroy all the other conserved quantities, different perturbation can have different effects. What do I mean by this? That is, for example, you can have perturbations that somehow disturb less the solitonic structure, and there is something remaining about this quasi-integrability of the dynamics. So this is an example. So if you take the total chain with some quadratic perturbation, take Z equal 2, just to, what you see is that, okay, just show you this. This is the the Fourier transform of the energy correlation function. So it's the thing that in the anomalous case will display a singularity at zero frequency. And you see that if you take this z equal 2, so this quadratic perturbation, there is indeed a very large regime in which this correlation function decays as a power, until eventually it crosses back, there is a crossover to an exponential behavior. So it does mean? It means that transport is very correlated. So these solitons, if you want to use very simple words, they recall a bit their independent particles nature for a long time. Then if you take another perturbation, for example, you take a quartic potential, which has the same number of conservation laws, the situation is different. The correlation function is just a Lorentzian, meaning that the decay is very fast. So this is the first message about perturbed integrable systems. Now let's go to the case in which I apply a perturbation and I keep the three fundamental conservation laws. So as I said, I would expect this to behave as an anomalous system, so an anomalous transport in the KPZ universality class. So with an exponent of the conductivity L to 1/3. So, is this the case or not? Okay, now I want to show you that the situation is a little bit more rich. And I will consider, again, two perturbations of the Toda chain. The first one is a simple one. You just take the standard Toda and you just change a bit the masses. So you, for example, you take masses that have two values, like the atomic chain that we study when we study optical branches in a solid state. And the difference in the mass is very small. So it's almost taught apart from a small modulation of the masses. This modulation destroys, at least, makes the system chaotic, destroys all the integrability properties, but it keeps the three fundamental quantities: energy, momentum, and the volume stretch. Another possibility is to replace to add some nonlinear, some stochastic dynamics. So instead of adding a nonlinear term, this is a slightly different type of perturbation. It's more like a noise, but a noise that conserves the three basic quantities. For example, you can imagine to have a Poisson process, a stochastic process, that just exchanges two velocities at random from time to time. No, this conserves the total momentum, conserves the energy, and conserves the length. So you may think that on very large scale, and this is indeed what happens, is morally similar to having an H prime perturbation. The parameter delta, for example, controls the distance from the integrable limit. If delta is 0, we recover the standard total. And the rate in the second model, the rate controls the distance from the integrable limit. So what happens? This is just a numerical simulation. So this is just the atomic Toda chain. So I simulate the conductivity with the method that I explained you before as a function of length. So if the system would be anomalous, like I expect, this quantity should grow as a power of the size with the exponent L 1/3. Now look what happens when I start with a large perturbation. This is indeed very compatible. So delta is equal 1 means that the masses are very different, so the perturbation is strong. And indeed, you see, apart from usual finite size effect, this line turns to a line to the expectation. But look what happens when I decrease delta. So I go closer and closer and closer to the integrable limit. This quantity, this curve flattens until I have a situation in which it seems to converge to a constant. So what's happening here? Does it mean that close to the integrable limit, the system becomes a normal conductor? This would be in contradiction with the general idea of universality, based on this KPZ approach. So what does it mean? What is the physical origin of this behavior? The idea is, I just explained in very simple terms. Suppose you have an integrable system and you have your quasi-particles. So if the system is unperturbed, the quasi-particle travel more or less freely. You switch on a bit of a perturbation. Think about of the perturbation as a kind of mechanism that induced a finite mean-free path, like you do in kinetic theory. No? So your quasi-particle have a finite mean-free path. Now, you would expect that if the perturbation is very weak, the mean-free path will be very large. No? Like in a standard gas, interaction is very weak, mean-free path is very large. So, what do you expect? If the system size is much smaller than this mean-free path, the system will be ballistic. The quasi-particle will just travel, they will not have any scattering. If you overcome this L, so if the system is large, you will enter what I call a kinetic regime. So in this case, this quasi-particle will just diffuse. And this will be a standard diffusion, presumably, no? Because you will not see the longer scale effect. And then you should have, for even more larger sizes, a crossover to hydrodynamics. If you think a bit, it's like the usual kinetic theory. When you start from Boltzmann equation, you go towards Navier-Stokes. No? So you have three regimes. The kinetic regime, in which you establish your equilibrium. Then you have the hydrodynamic regime, which large fluctuations slowly relax the equilibrium. So it's very similar here. So the idea is that you need to overcome this L star, this typical size, in order to enter in this anomalous regime. So you have three possible regimes depending on the size. This idea can be made more rigorous, and you can give, for example, an estimate based on very rough arguments. So just assuming that the mean-free path goes like an inverse power of if epsilon is the perturbation, suppose that it goes like an inverse part of the perturbation, which seems reasonable. Now, what you see that you can just give an estimate, which is this given here. So this L star is an inverse power of epsilon. So you can immediately understand that this quantity can become very large, close to the integrable limit. So it means that it may be very difficult to reach this anomalous hydrodynamic behavior. And this may explain why in the simulation you don't see it. Okay, just skip the details. It works very well with the numerics. I just skip this. I just show you an example, and I close with this. So it works very well for the perturbed toda. No? Now you may go. This is what I show you here. So if you look, for example, at this curve, you clearly see that there are three regimes. There is a ballistic, a diffusive, and then hopefully there is an anomalous behavior. You can go even a step further. As Giancarlo Benettini always say, if you take the Felipe-Pastola model at very low energy, the alpha plus beta model, so the one with the cubic term, this is very close to toda. No? There are many evidences of this. So you should look at this model instead of a standard phonon system perturbed by nonlinearity as a kind of toda system perturbed by some correction. So you immediately see that this in this model, the same time of reasoning that I used should apply, because I can consider this FPU model as a perturbation of the toda model. So it should have the same phenomenology, if my reasoning is correct. And you see that the simulations are pretty in good agreement with this idea. So if you decrease the temperature, which is in a sense is your perturbation parameter, because the lower the temperature, the closer you go towards the toda limit. And you have a crossover from the anomalous behavior, which is not exactly what you expect, but at least very close, towards this kinetic regime that I explained. I don't say anything about the harmonic chain. I just don't say anything about other models. And I go to the conclusions. So the idea is the following. Conductivity in one-dimensional systems, like I explained you, with three conservation laws, is generally anomalous. If you are close to the integrable limit, there are more complications due to the fact that you may encounter this intermediate regime, which correspond to the standard diffusion of quasi-particles, and only at very, very long scales you may observe these anomalies. And I didn't mention this, but the same thing holds also for fluid models, not only for oscillators. And it's also when you take a quasi one-dimensional system, which is also important because imagine you have a system constrained in a kind of box which is very long in one direction. There is indeed the same type of phenomenology. So this confirms that this scenario is indeed general. And with this, I stop here, and thank you very much for listening.
Thank you very much. There are questions? Question? I have a curiosity. When you introduce perturbation, you impact the fact that solitons, when have interaction, shift their phase. How impact the perturbation on this process? Which is the...
Okay, my approach was purely phenomenological because I don't think this is easy to compute, at least not for me. The idea was just to say, okay, this quantity, this scattering rate has to go to zero for when the perturbation goes to zero. The simplest ansatz could be to assume that it is a power law, something like, where is it? Like this. So to assume that the mean free path is inversely proportional to epsilon to some power. If you go to the limit in which the energy is infinite, so the system is made of hard particles, you can indeed make an estimate, because you can, in this case, they are just free particles, and you can assume this kind of Langevin dynamics. And you find that indeed, if delta is the mass differences in the two, this scales roughly like 1 over delta square. But of course, this is something that holds on in the limit of infinite energies. So our surmise was that more or less this kind of scaling should hold also at lower energies. But of course, it's just an argument. Maybe that this becomes, I don't know, delta to some minus something. Okay.